Hello everyone, thanks for coming here to the next LLVM social in Berlin. Despite the good weather outside, there's a few people here, that's great. I want to talk about something I had in mind for at least the last 6 months, since I saw a presentation of Teresa Johnson, who talked about ThinLTO at the CPP-Con last year. And I directly had a lot of associations with problems we have when just-in-time compiling code. And I always wanted to explore what or how good this can be used or abused for JIT compilation. And that's what I want to present today. It's kind of a case study, so I did a little prototype that does some of the things I wanted to try out. And we will have a look at the code after the presentation. Then you can ask all questions you want or see how it works. And until then, I would go with smaller examples, because if I go into all details, I will never finish. So, ThinLTO. What is it? Or first, what is LTO? In a nutshell, LTO is link time optimization. It's also called whole program optimization, or cross-translation unit optimization, or monolithic optimization. That's all the same thing. And it tackles the problem that compilers can only, for example, inline code that they see, and they usually only see one translation unit. So, for example, in C++, if you have definitions inside a header, then the compiler can inline them and optimize across function boundaries. This is not the case if the definition lives in the CPP file, because this is not something the compiler sees. And here the linker comes into the game, and the linker could optimize that because it has the full picture over the whole code. And traditionally, LTO is very expensive and it scales very bad. What it does is it merges all code that exists into one, in LLVM slogan, in one module, and optimizes that module. So that's a lot of stuff then you have at one point, and that's not a very scalable thing. The first thing that it requires definitely is to have IR code in object files. So instead of writing binary code into object files, the compiler will emit object files with IR code, and the linker has access to this IR code and can optimize on that. What we get then is not real native object files, but wrapped native object files. There's some details. You cannot, for example, query symbol names with the normal NM tool. For example, you need to use the LLVM NM tool to have a look into them. ThinLTO on top, or compared to that, it's first of all very similar, but it tries to fix that problem that LTO doesn't really scale. With ThinLTO, the compiler also emits the bytecode to the object files, but it also adds summaries that it collected during compilation in the call graph. And those summaries are really compact and only deal with global unique IDs instead of real names. So it's a very compact and easy to traverse data structure. The linker can then read all those summaries and combine the summaries of all translation units into one global combined index and do some analysis on that. It's typically called interprocedural analysis. And in ThinLTO, this stage is called thinlink. The thinlink itself happens sequentially and cannot be parallelized, but what happens afterwards can be parallelized on a per module basis. So each translation unit can be compiled or optimized individually, independent from each other. This is called the thin backend that does that, and during this process, for each module, the definition that it needs, or that it could use from other modules, are imported, and then interprocedural transformations are executed with the whole view or whatever the module needs. Very short, the process is, first step, we have a module, and this module has few dependencies. Let's call them module A, B, and C. And in the first step of the ThinLTO backend, we will import all the definitions that we need. We have declarations for them usually in the module, but we import the definitions for that, and then we have them available in the translation unit scope. If those dependencies have dependencies again, we will also import these dependencies and so on, and there's a little threshold that tells, okay, now we stop importing because we don't want the whole program in our module. And the good thing here is, when we materialized our main module, we don't need to materialize all modules in all backends. We can use this lazy materialization and only load the module blocks and materialize the blocks on demand as we need them. So it's quite performant, and that's what ThinLTO also wants to be. It wants to be much more performant than monolithic LTO. In the second step, we will use the imported definitions to optimize our module. This is typically, or this is mostly inlining, and optimizations following on inlining. And after we're done with that, we can drop what we have imported, and our module is done and can be passed to the final link stage, where the linker, just like every other linker, summarizes everything and emits a executable or library or whatever. The benefits of this is it has very small overhead compared to monolithic LTO, because, as I said, the summaries are very compact. They only deal with globally unique identifiers, not with real names, and it's made to be combined very fast. So the whole thing scales much better than monolithic LTO because the actual transformations run in parallel. And it's incremental in the way that we can cache object files in the linker and check if we need to do anything on these object files, plus whatever your linker does for incremental linking. So it may link certain object files together and others not, and build groups and stuff, but that's out of scope for LTO. The speed up is typically close to monolithic LTO. It's always hard to measure something like that, but in the presentation she lined out very well on many different architectures and examples that there's really good optimization going on there. And it's very good for development, because you don't do manual optimization that much. For example, typically with C++, the good question is always, should I put this definition in the header so it can be inlined and it will be much faster, or do I put it in the CPP so I have a better program structure and my code is much more readable? And this typically leads to long discussions in reviews, and everybody who knows that knows that that's not really a good thing. On the command line, it's super trivial. You just add this FLTO thin flag and compile link, or do all at once with Clang. That's another note. This is only implemented in Clang currently. It's not available in other compilers as far as I know. And it's also not really standardized now. I think the bitcode format is going to be standardized soon within LLVM, but not outside the universe of LLVM. If you want to know more about this, I can really recommend this talk. This is really clear and points out a lot of detail that is really interesting. And there's also a very good blog post about it, and of course the documentation in the Clang, on the Clang website. The next point was incremental compilation. What's that? it's basically we only want to rebuild what is necessary. We don't always want to rebuild everything because we want to reduce compile times. What is necessary is, yeah, typically necessary is what changed and everything that depends on what has changed. There's a little terminology, I don't know, thing between incremental linking and incremental compilation. So incremental linking is basically the same, but the granularity is on a translation. So a translation unit is the atomic entity that we have in incremental linking. We cannot rebuild a part of a translation unit. And incremental compilation typically is referred to something that has a higher granularity, so it has a lot more entities to kind of manage during the compilation process. And complexity is in C-like languages where we have translation units, typically incremental linking is much easier to realize than incremental compilation. And this is probably also the reason why incremental compilation is not really used in practice today, or at least I don't know where it is used. We'll see a little thing about this in a second. First, I want to make the note, this is about compilation time, not about the performance of the compiled program. So the point is reduction of this time, but the mechanisms that we need to track all the entities that exist also causes overhead. And it is very easy, if the number of entities grows, the overhead grows and the whole thing eats up all benefits. So that's the typical problem. And before you try that with LLVM or anything else, it's usually a better way to just link dynamically to reduce turnaround times. So if you link against LLVM, for example, it's much easier to just dynamically link against the liblLLVM dilib instead of linking statically all the time during development. And it's just a good recommendation to have a CI or something that always builds everything also statically, because otherwise you can run into a lot of issues. One point where incremental compilation is used or is developed in a practical compiler is the Rust compiler. And this compiler has a granularity, just to make an example, of an AST node. So if only one AST node changes, it can track the dependencies of that node throughout the whole program and can say, okay, this is what I need to recompile in the end. And you can imagine that this gets very complicated very fast. And imagine all the structures that you need in the background to track all this information and to save or to save intermediate results and to manage all these structures. What it actually brings is hard to say. There's a blog post about the Rust compiler that says up to 15% or more, which can be anything. They also make a joke about this, I think. I think conceptually it's a very promising idea to track what has changed and what needs to recompile. And if you think about development tools, it's a very good idea to not always do the same and start from scratch, but see what is actually necessary and what needs to be recompiled. But it's a kind of academic research thing. It's not really, there's not a really practical demand for this when it's only about incremental compilation. The blog post you find here, and if you have any more questions, then we can answer them, hopefully. But so far I would continue with the JIT compilation point, because that's what I wanted to point out. A JIT compiler does both. It compiles and links, so it is hard to say whether it's incremental compilation or linking. There is no simple separation. one note about the JIT compilation is that our source representation is the IR code and not the original source code like C++ or Rust. When we see monolithic JIT compilation, I called it monolithic, like monolithic LTO. We would have some kind of interface, and we would recompile everything every time and reset all state and restart from scratch whenever we change something. So we would probably have some interface where we can submit source information, like this is the files we use, this is ABC bitcode here, via file names, the description, whatever. And we would probably have an interface for requesting callable functions. So we would give it probably a mangled name or name plus signature or whatever, and it will figure out somehow, okay, this function lives in this file and I need to recompile that, and it has this dependencies, so I need that. In this case we have modules A and B, and they need to be compiled in order to link or to compile that function and resolve all dependencies, and we can obtain a function pointer from that and return it, or we return an error if there's something missing. And if we want to do that, or if we think about what would it mean to compile incrementally in this situation, is okay, now we have this function x that we already provided, and now we request another function, and this is called y in this example, and we figured out, okay, it lives in module C, we want to compile that module, and it has actually a dependency to our function x that we compiled already earlier. So it will probably compile this module C and resolve the dependency to this already existing function x. The problem that we have now here with the JIT compiler is time. And everybody who has heard of that knows probably about this, that whenever time occurs something, it's where things get really complicated. One more note before that is that if you see that, you already see that this will prevent inlining. So as we compiled our function already, and we will reuse it because otherwise it would not be an incremental compilation, we cannot inline function x in function y. When we now compile that and everything is good, that's fine, but what also could happen is that our module B changed in the meantime. So what would we need to do? We would probably reload B into our cache, whatever, compile another version of the module B, compile a new version of the function x, and link that function x to y, or resolve the dependency in function y. Why would we do that and not only leave B on disk unchanged? Well, maybe C has changed, right? And it wouldn't work with the old version of x. So we actually need this new version of x. And now we are in this conflict that we say, okay, we already gave out a handle to our old function x. What should happen to this handle? Can we still call it or not? Can we update it? We probably need some management infrastructure for that already. Like, this is already a situation where you cannot just, it depends on your use case, of course, but you cannot just go on and don't care about this. So we kind of need quite some housekeeping to realize a incremental JIT compiler. We need to track changes on disk. We want to determine where our function lives, in which code we need to compile actually. We want to decide what needs to be recompiled if something changed on disk. We want to link against existing code because we don't want to recompile everything. We need to determine which static initializers we need to run for which global variables that are new. And we need to invalidate existing function handles that we already provided in some way. Maybe we can even rebind them to the new version if they are compatible. So this is where ThinLTO comes for help. ThinLTO module summaries provide us module hashes where we can check if the module that we have in memory is still the same as the one we have on disk. This is very easy because we just need to reload the hash from disk and compare it to the hash we have. And it helps us to determine which source dependencies our function has. We can, for example, calculate the global unique identifier for our function and just go through the summary and see in what module it is available and just compile this module. So this is already a really good thing, because otherwise we had to materialize all our modules, go through all the modules and search for the function name. And that's already quite some overhead when we in the end realize, okay, we don't need to change anything. Actually everything is up to date. That's a bit of a pity. So with ThinLTO, we get all that. We can check for early exit if we don't need to parse anything extra. And we can compute imports that we will see later, like function dependencies that we will have. So we'll remember that we need quite some housekeeping for that anyway. But more importantly, we also run the code. So the question is it possible to preserve the state of our function that we already compiled? Like if it has a global variable like a counter or something, and it counted already and it has a number inside, if we recompile and everything is fine, could we reuse that state instead of emitting a new global variable that has a reset state? So that's what I would call a stateful incremental JIT compilation. And it turns out that one thing changes in our list, and this is the global initializer question. What we actually want to do now is to rename global variables that we already have as an instance in memory and resolve the reference that we compile in our new codes to the existing one. And the mechanism that ThinLTO gives us for this is called name promotion. This is very, very useful in our case. Name promotion handles the situation where we import from other modules and we need to see if the imported code has a global variable that conflicts with something that we have in our module code already. The name promotion in ThinLTO backends, this is a very simple example. What could that be? So we have can you read the code? It's a little. Yes. We have two function declarations at the top: read global, write global. We have a global variable in our main translation unit, and we have a main function that calls both functions, adds the value of this global, and returns that. And if we compile that, we should get something like 11 in this case. Down here we have this global CPP that gets also compiled and linked in, and this also has a global variable with the same name as the one we have up here. And it has actually the definitions for read and write global, which are straightforward, so I don't need to explain that. What will happen if we wouldn't promote external variable declarations that we import is that these two names would collide, and we wouldn't know which one to resolve if we want to access one. So
why do the linker not complain?
It's a static definition which is only valid in the translation unit.
But why does it prefer the one which is 11?
So what happens here is...
So if this global, the functions, they have a static scope, it should work actually with global variable of global module, no?
So what happens here is, in the main function, we first write the number 1 to global variable down here. So here this will set global variable to 1. Afterwards we read this global variable, which is now 1. It returns 1, and we add our own global variable.
Sorry,
which is
okay, yeah, I missed the, yeah.
Exactly. So, and this should return 11. So what we do instead is when we import this global CPP into our main translation unit, is we rename this global variable to something that will not clash with anything in that module, at least for a very, very, very good likelihood. No, I even think it's a defined specifier. If you have like .LLVM dot, it is some convention that this will never collide actually with anything that already exists.
But LLVM does it already, you know?
Exactly. This is implemented in the ThinLTO backends.
But I mean, by default, if you read some modules into context, you reuse the same context to read modules, then you will not have collision anyways.
I don't know if this is the case.
That's the case as far as I know.
It renames on merging modules.
They will have like global var 2, 3, and so on.
Yeah, that's possible. Yeah, that's perfectly. The point is, I don't want to use the module functionality of LLVM because it does not provide me all the codes that I want. What the ThinLTO implementation does is I give it an import list, and it will do all the hard work for me. It will adjust like linkage types and things like that. And it will only import the things I actually need. I don't want to import the whole module because I would do the same as monolithic LTO, to merge everything into one module and optimize on that. I just really want to import I also don't want to import the definition here. I only import the declaration. So this is how the main CPP would look like if it was C++. That's why I wrote pseudocode here. Obviously it will be IR code, but it's kind of this thing. And this name will refer to the global variable in the other translation unit. So we still compile both translation units, but this name will refer to the other one in the other translation unit. And so we don't initialize it here even. Like we just have a reference to that. But now we have our read and write global definitions, and we can inline that, and it will be probably just return 11 or something like that when we optimize the module. And it happens that this postfix that the importer adds here is the hash of the module where the global variable comes from. And this is very useful for us because, like a regular linker, we can now in the JIT also use this hash to find the module where the symbol definition is. And this is great. Another thing is also great. It's that if we modify that file and add just a line printf something, we will now have a different module hash. And if we imported that again, we would have a different global variable specifier. So we could already have like a revision management or revision distinction between which global variable was imported from where. Like if that was the first revision, this is now the second revision with a different module hash. This is very interesting because if we manage our modules that we have available for compilation in revisions that we compiled, whenever we recompile the module we get a new revision, then we can already on simple resolution time decide, okay, this comes from the old revision actually. That's a very useful thing for stateful compilation. The problem is that, let's say this works very well also for this use case. The problem is if we recompile this global CPP, the importer actually doesn't know that we already have a revision for that. And it doesn't care about that because when you ThinLTO, it always compiles everything or it always compiles full translation units, and it doesn't care whether there is a global value that I want to reuse somewhere with some state. So it will not care about this. And what I did in my prototype is just to hack that on my own, that if we recompile a module and I realize, okay, I already have this global variable in memory with a state, then I rename this in the module. But that's kind of a hacky thing that would be better to solve if a little detail would be different, which is it's ThinLTO, it doesn't care about this, so there's nothing wrong. It's just not so well abusable for stateful incremental compilation. And the point here is that the module summary index that we built in the ThinLTO process has keys for its entries that are the module IDs and not the module hashes. With the module IDs, I can find the module very well, and it's all great for ThinLTO. In our use case, or in my use case, this would be better if this was the module hash, because then I could associate this much better and have one index for all revisions of my compiled modules. It looks a bit like that. So if you have, again, these ABC sources and we compile the first revision, A1 and B1, we can build an index for that. And if we recompile another revision because we want to have C now and, for example, B changed or something like that, then we can recompile another revision, but our index will only be valid for the newly compiled modules and will not have the summaries of our old modules, because it's the module ID that is inside. It's also not useful to merge them or anything, because we couldn't decide which one comes from which revision. If the module summary index had module hashes, then we would exactly know from which revision and from which module our summary comes. But this is not easily possible with the current implementation. So in this case, we can import from A and C if we want to recompile B. What would be great is if we could recompile and have also this in our scope, and we could import from all the revisions that we already have. Other things that we can use, like this was one example now that I wanted to grab because it's one of the main things. Other things that we can reuse from ThinLTO is this get lazy bitcode module, where we don't actually parse the whole code of the module, but just a few section headers, and then load on demand their content. We can perfectly use read module summary index that also just reads a small portion of the bitcode to obtain all the global unique identifiers. And we can use the dat symbol stripping, which is really great because we can just define our functions that we already queried from a module. We can remember the GUIDs and say, okay, when we recompile that, we just add something to that, but please keep intact the things we already had. So we want to query them again. If we have two functions that we want to run from one module, and we recompile the module, we have then, for the second function, then we have both in there. So this dat symbol computation is very useful to preserve them, but to throw away everything else, but because we want to compile as less as possible. And of course we can use this cross-module import, which is like ThinLTO actually computes the cross-module import for all modules, not only for one module. We actually only care about one module at a time, but there's also one function that does exactly that. That's perfect for the stateful incremental JIT use case. So the overlap of ThinLTO and our JIT is that both actually require a global view of the program. Both are computationally expensive, and if the project is big, then also huge in scale. Both run in kind of 2 stages, which is a global analysis, for example, to find the module where our function is in and which dependencies there are, and to prepare everything for compilation in the JIT case, and a per module recompilation, which is the thin backend for ThinLTO and the recompilation of all modules that we need to update and create new revisions for in the JIT case. And also the focus on optimization of the compiled program is actually a very good thing, because I mean, when I talk to people, they usually argue, okay, but why do you do that with a compiler, and why don't you just write a virtual machine or an interpreter or whatever that does exactly that? Like, that keeps your state intact and adds new functionality to it when you change code. And actually, things like that do exist. The problem with that is that it does not scale. So if maybe you know this Omniscient debugger implementation for Java. There was an experimental project for that, a debugger that tracks all states that existed in your program at some point. And if you use that with real-world programs, it's like a few seconds until you cannot use your program anymore, because it needs to track so much data and so much state that it just slows down everything a lot. And if we keep an acceptable runtime with a high granularity or a big number of entities that we want to track and manage, this is kind of the key issue that would be necessary for a useful, stateful, incremental, just-in-time compiler. So this is actually a very good property of the ThinLTO code. The short-term goals that would be great for this project is to hack Clang so that it emits hashes in module summary indexes or in module summaries. It would be great to build an infrastructure that is really targeted towards incremental compilation based on the implementations of ThinLTO. It would be great to extend the management infrastructure that is in my prototype. It's very, very small. It will not support anything. Like, it's basically for my examples and not much more. And if it could handle cases like we compile a function and then we change the code and then we recompile the function, but now it has a different signature. Like, things like that are really complicated, and that needs a good infrastructure. And it would also be great to have to load, instead of single files, to load a complete project description, like a Ninja build file or something like that. That would also be nice. It's not there yet, maybe someday. The long-term goals are not that realistic, but maybe at someday this would be possible. I mean, usually it needs a proof of concept, and if something is a good idea, then people jump on the project and say, yeah, I want to work on that. One great thing would be to have a Git-like revision management system for program state instead of only for program code. You could, I think at least, it's definitely, all of this is up for discussion. I would be interested in all of your opinions. But I think it would be possible to fast forward merge a lot of side effect free changes, like the printf we saw. It actually has side effects, but we know that it will not change the behavior of our program. It would be possible to fast forward merge this in our program state, and other changes that maybe create conflicts with the state we have already in our program could be resolved by the developer, who commits a new code into a running instance and now the compiler says, okay, I can do that, but what should I do with these global variables? You reinitialize them, or you change their type. How should I map these things? So this would be something that the developer could decide. And the obvious benefit of this would be that the edit compile test cycle would be much, or it wouldn't exist anymore actually. It would be a edit compile test cycle or something like that. It would be great to save and restore state snapshots of programs. Like my project is actually the best example for that because I had a lot of hassle with that. If you have like a controller that runs certain cases and then in the 20th line you have a bug and you want to change that, and you want to investigate what is the problem, you set breakpoints everywhere, and then you need to rerun your code, and it will come by all these breakpoints already 10 times before you want to hit that. If you could just store your state in that point, change the code, and let the new code work on that state, that would be amazing, I think. And if anything fails, we can still fall back and restart the program. What would also be great is to emit summary data to the executable. So all the data that gets collected could also be like debug information shipped or stored to an extra file. We could even think about packaging the JIT as a dynamic library and use it like a sanitizer and link it into existing projects and handle state restoring and saving with this dynamic library. And it would of course also be great to implement support for like developer tools that could use all this functionality to modify executables based on the program state summary that we provided. This was all the slide-based things that I wanted to say. I hope that's a lot of stuff that could be discussed. That's it. Let's dive into the code and see if you have any questions or not. The project is here on the link. I already have it checked out on my computer. I only tested it on Linux, so...
Can you make the font larger?
Yes. Let's see. So Control Shift O. So okay, the project consists of not so much stuff. We have a main CPP, which is kind of a driver program or driver function, the main function. And we have the main implementation in the ThinLTO JIT. And there is a lot, the management, the revision management code is in the parent module record header. And we have some arrows defined. I tried to use the LLVM arrow implementation, which turned out to be a really good thing. When we run the program, you will see it because it will fail at some point where I didn't finish the fix yet because of this function signature change, and it just uses under the hood. It just uses a simple org JIT implementation that is more or less a copy paste of the JIT from scratch project that I have on GitHub. So let's see what main does. So we have a few helper functions up here, and I can scroll. It always works like that. It takes a file. I prepared files on disk that represents different code states of implementations. They look, maybe I find them quickly, maybe not. Here, example. So in example source, there's a few CPP files that have the typical example code that doesn't depend on too many things, and it's always the scheme that there's this integer distances function that gets two arrays with a defined number of items, and it calculates within the arrays between each pair of values in the arrays how far the absolute distance is. So stupid stuff, but it does something that we can observe, and the critical point is always that the result array is allocated in a handmade allocator, and this allocator has state. So when we recompile anything here, we want to reuse the state in the allocator. And this, for example, changes here into this, which is maybe even not correct. Oh no, it is correct. It does not return the value anymore here. This was the change. So here, this function now is a void, has no return type. And the problem, the special problem with that I did not implement yet in the prototype, is that this is not represented in the mangled name of the function. So before it returned an integer pointer, and now it returns void, but the name is still the same. So we cannot determine that it changed. Actually, it's a bit of a pity that the return type is not encoded in the mangled name. But that's the case, and we cannot change it. So what the main driver, or what I did before, is run this script that is also part of this project, which compiles these CPP files into these S files. And what I do in the driver already all the time is to take these S files and copy them to the same location but without this prefix. So it's always integer distances S or custom int allocator S. And so this is the way to keep the module IDs the same. Because that's the problematic thing. If you compile from different source files, if the name always included the prefix, then the module ID would be different, and then it would be considered a different module, and that's not what I want to have. Okay, so let's go through the example a bit more. It's a bit slow here. So what we do is we first move in place copy in place these integer distance and custom int allocator functions. Then we add them to our runtime. We add also a function that bitcode file that doesn't exist. Should be no problem as long as we don't need it, or as long as anything is fine. That should be no problem. And then we say, please runtime compile me this name as this signature, and it will return a function handle that we can call a call function on, and this will call the internal JIT compiled code with the given parameters. And here we see, okay, we first compiled the integer allocator function, and then we compile the integer distances function, and this one calls the integer allocator. So this is now exactly the case that we have a function x already compiled and a function y that wants to call this function. And what I did instead of calling the function here, or what the JIT infrastructure, because it uses the ThinLTO functionality, does is it realizes, okay, we already have a version of this function, so did anything change in this module? No, nothing changed in this module. We don't need to recompile the function or the module. We can leave all handles that we already gave out. It leaves them intact, and it will only compile the second module, the integer distances module, for us and return the function. The point is what we do here is not calling the custom integer allocator function. This will be imported through the ThinLTO functionality and inlined in our integer distances function. And because we know that nothing changed in this other module, we can inline that, and it will still be regular valid code. And we will in a second see how this looks. The next example is that we recompile the same function again. This is the case that we now realize, okay, nothing changed. We can very quickly see that we don't need to do anything. So that's the early exit case. And what happens down here? We call all these functions and dump their results. And then we change the custom integer allocator and compile our integer distances function again. So this will now realize, okay, my own module did not change, but the other one changed. So I need to recompile the other one. I need to invalidate the handle that I gave out for this other one, and I need to relink my own function, or no, not relink actually. Sorry, that was wrong. I need to recompile my own module because it depends up on this module. So it will again import all the functions into the integer distances module, recompile this, and give me a new handle. And the other handles will be able to rebind to that new implementation with keeping the state of the allocator. And the output is always, here's the helper functions. So here's the functions that dump our results. By the way, little side note, what the functions return, or what the handle, the function handles return, is not the return type that we specified, but expected the return type that we specified for the case that we cannot call our function anymore because it's outdated. Then we will get a yet to be defined error that says, hey, your function is not valid anymore, you cannot call it anymore. But what it always does, the dump memory function will always dump. So if we call the custom integer allocator from here, it will always dump the address that we just allocated. So if we allocate 3 items, then it will dump the address of the first item that it allocated, and it will increment the counter, and next time it will dump the next address. And here we will always see the results that we get back exactly. And the last thing before I run it is this change in the custom integer allocator. Sorry for that. So this is the original code for the custom integer allocator. It has 2 static variables in the function. So that will be global variables in the global variables in the global scope in the IR files, and they want to be reused. And the change that I do before this third step is to add a printf here that dumps out, I'm allocating items at position whatever. So if we run this now, maybe it's not so good to run it here. No work to do. It will run it here in debug mode, and it will be loads of things that happen, and we will not see the result. We can do this in a second, but for now, let's do that here. Oh no, let's run it from here. In examples. Yes. Hopefully, maybe I can get this a bit bigger too. So what we have here now is we first called the integer allocator function, and it allocates at this address, which ends in 6464, and then we call the integer distances function. Stop. This should not be the case. Sorry. Task switch doesn't work so here. So let's have a look here again on what we do one after the other. Exactly, okay. We will call the allocator and allocate 3 items. And then here, down here, we will call it again before calling the integer distances function once, and then again. So this should allocate 3 items. This should allocate 3 items, just 24 bytes every time. And this should allocate 3 items, this should allocate, and so on. And we should have the output here now, which is, okay, that's 64 and 76. Is it 3 integers? 12. 3 times 4? Yes, 32 bits per integer. This is 76, 88, again 12 bytes. And this allocates now at 6500, which is again 12 bytes further. Then we have the change that we now dump from within the JIT compiled function of the custom integer allocator, and this writes out, I'm allocating now position 12, 13, 14. Then we call this again, and it from the main function, and it allocates from 15 on, and then 18, 21, 24, and so on. And here we get the error that unfortunately it doesn't support changing the function signature yet. That would be great, but at least the first 4 examples should work. And I don't know, is it interesting to have a look at the code? Or, I mean, it's a lot, and I don't know how well it fits on the screen. Or do you have any questions first?
We can try to look at it.
Yeah?
If you don't like it, then we can stop.
Yeah, let me know before you all fall asleep. Then I show something else, or I don't know. Okay. One thing that is very important for the project is that, like, this is the. Where do I start? So the ThinLTO lazy org-JIT runtime is a bad name for the runtime, but it's somehow readable. It has the JIT inside as a component, as a member, and we define the optimize module function here. And for this function, we define the inlining threshold as a very, very, very huge number, because I did not implement the case where we want to resolve a function name that was not inlined, because this would not have the module hash attached to it again, and then it would be more effort to find the function, and I didn't want to think about this situation yet. So what it does now, it will always inline. Whatever it gets, it will inline. And that's pretty good for the example. We can maybe have a look at the code that gets compiled. So this, or at least we can start doing this now, because I think my virtual machine on my laptop with the screen attached is pretty slow, and it will. This is now the downside of dynamic linking against the LLVM dilib, because it will all do all the work at startup time. So that's now a bit slow. Usually it's not that slow, but I don't know what's wrong today. So we can use the time to look at the header, which has almost all functionality. So let's remove that again. So this is the type of the function handle that, yes, exactly, that's where I wanted to stop. So here we are in the situation where we stopped because we arrived here and we have this signature change thing. And our output looks like this. It's a lot of code. Yeah, it's all like sometimes I change I use this command line interface that LLVM gives us to specify which debug settings I want to dump. So I only dump my own debug and the function import, but this is already so much, like I don't want to split it up into more things. But it would be a good talk to show me how this is done easily, because that's what I always struggle with. So let's go through all this code here. And I like Visual Studio Code a lot. It works well with LDB and Clang on Linux. It's really nice IntelliSense and Clang format and everything included. The only thing is that the command line output is sometimes screwed up, and you have like strange reordering of the output. That's a bit bad, but it looks okay here. Okay, so we compiled the custom integer allocator here, and it has these two global variables that get initialized here. And this should be the only time when we initialize them, right? It should be later, it should not be internal global with 0 initializer. We want an external hidden global without an initializer later. But this is the symbols that we will have all the time in our first revision, and we use them straightforwardly here. There's nothing much to say about that. The interesting thing is here, no, also not. Now first the optimized module, it's not much different for this case. Then we start with the integer distances module for the first time. So here we see from what modules we import functions, and this is the custom int allocator, and it will recognize there's nothing to do for it, and it will only compile the integer distances module. It will say what it is importing and what it is not importing. Yes, it imports the definition for this function that we want to call, but it does not import the global definition of these symbols. It does only import a declaration or a reference to these symbols. And they will be renamed, and this is what we see here. So this is the original symbol name that we want to have, and this is the module hash that we get. And now we have an external global without an initializer here. Same for the memory. And this is now the unoptimized, not yet optimized module, which is also straightforward code, blah 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 blah. And now this is the interesting point where we have the imported code for the custom int allocator. And this is not the linkage type that you see here is very special, because I don't know if this is used anywhere else or if it was invented for ThinLTO, but it basically says, okay, you have this here now for optimization, this available externally. You have this now here for optimization, but whenever you're done, I will throw this away again. It will not be part of your symbol table. You cannot do anything with that like you want. You can inline and that's it. Or maybe query metadata or something. And this gets now optimized, and here we have everything in one function, I hope. Yes, we already see we load from the global variable from the other module. This will be resolved to the symbol in our first revision of this module, and so on. We can have a look at the symbol resolution maybe at some point. This is just optimized code here that no one wants to read. If anyone can explain that, then I'm listening. But it's, for me, this is like, I don't know. It's a lot more code, but it seems to be more efficient. So, okay, and this is now our output that we saw at the very beginning of the terminal output. Okay, yeah, and then it goes on and recompiles this thing again. It recompiles the integer distances first. Like, that's an internal thing. How to in what order to recompile the modules is actually not important. That's also good, because we don't want to make a directed graph of modules which need to be compiled after each other, because then we cannot parallelize it anymore. And then we have a lot of work and a lot of management communication that's again overhead. So it chooses to first recompile the integer distances module, because the second module changed. And we added this printf, which is the string here. And this is another thing that I need to fix manually, because these local strings are usually private symbols, and private symbols are not in the symbol table, but we still want to access it. So we want, when we resolve this thing here, we want to go to the other module and look through the symbol table and find this string. But if it's private in another module, it's not, we cannot find it, so it will not be found. So I had to fix up the linkage types in the code before. Yes, so this is straightforward, recompiled and optimized and blah 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 blah. And now, oh yeah, this is my own. This is what I dump on my own. There should be more, but the output is a bit screwed up here. It basically said, okay, I recompiled your custom int allocator, but these are the symbols that we have already in a previous revision, but the ThinLTO implementation wouldn't recognize that, so I need to fix it up on my own and rename these definitions with the correct hashes from the revisions that we want to pick it from. And I dump that here, and then exactly. Now I have this in my custom integer allocator, which usually had, if we didn't this fix, it would have the 0 initializer again, which we don't want. But we want the reference to the external global in this case again. And the code uses it perfectly, and yeah, I don't know, the rest of the code is always the same. What may be interesting when it comes to the implementation? There you can see now we need to scroll a lot. There's a lot of management code here. Like, this is the function to find the right module for the function we want to compile, which is pretty straightforward. We go through all cached modules that we have and check if the module index that we loaded, the small thing from the bitcode file that we loaded for each bitcode module, has this GUID. And as soon as we found the first one, we don't know, at this point we don't need to know the function name or anything else. We just say, this module has what we want. So take this, and then we go on and query like dependencies and stuff. This is a bit later when we want to, when we materialized our main module for one translation unit, and we want to import the functions from the modules we depend upon, and we get this list of this import map. I store this in my module record, and we get it here and pass it on to this import functions thing. And this function importer is what we can just reuse from LLVM, from the ThinLTO implementation. It does the same thing, and I think it's one-to-one the implementation of the ThinLTO that I just copied, and like I throw away everything that I don't need. That's the only thing. But this will do the import. It will get the module, and it will import something into this module and return it again as module plus imports. But before I go through all these, I want to go to the main thing that runs all that. Because I think that explains a lot how it works.
I think it's starting to get like really complex. So
this is here.
I'm not following anymore. I'm not sure about the others.
Okay, then here is the entry again to what you heard before, because this is the function we call in the runtime, this compile function. We give it a mangled name, and it will find the correct module, it will recompile everything, it will manage everything, and then it will return a type function handle here. And this handle has the pointer to our just-in-time compiled code. And I just go quickly through that, and then if there's any questions, I'm happy to answer them, and otherwise I'm not bad. I'm not in a bad mood, you can.
Not yet.
So the first thing is we update all the module indexes from the bitcode files we know we need to consider somehow, and there may be some errors coming back, but as I showed in the very beginning, there's also one bitcode file that doesn't even exist. So it will report an error here, but we don't know yet if this is actually a problem or not, and there the LLVM error infrastructure is really well, because we can keep it for now and see later maybe this is the reason for some subsequent error. So I don't have a diagnostic system here. I just join together all the errors that occur, and once something is fatal, I return all of them. And otherwise I say, it doesn't matter. Maybe it should be a warning or something. Exactly what happens? We get a mangled function name. We calculate the global unique identifier for it. We find the correct module ID that has our function name. Then we link the combined index of all module summaries that we have. And in this would be the new global index that we would use for all subsequent calculations. This is like ThinLTO stage 1, ThinLink still. And then we check here if we have a new module that we did not compile before, and if we calculate our cross-module imports and nothing of what we get depends on anything that changed, then we are done. Then we can already leave and say, nothing changed, here's the function, we already have it, nothing to do. So this is a very short thing that we can only do because we have this module summary indexes. Then we calculate the diff between the last global index and the new global index. We collect all global preserved unique IDs from all the modules that we have already that needs to be preserved in the next compilation. We remove those GUIDs that were removed in the new index. Then we compute that symbols in our new global index. I do not use these preliminary imports here because they have usually for my main module I could use this map, but I don't want to do that because it contains much more than we need. It will not have all that symbols stripped. So I do it again later for all the same, actually. So then we create new revisions for modules we want to compile. We adjust the linkage for those functions that we want to preserve. They should not be, they must be, if they have local linkage, for example, if they are also private functions. There was some reason for this. I think it's also the same, doesn't matter. We add the function name to our module record, and now we check, okay, which modules do we actually need to recompile? This will figure out which one this has. Then we update the hash, our lookup table for which hash belongs to which module, and we recompile our modules and query the address, and then we're done. There's maybe this is, well, maybe this function is interesting, maybe not. So it will get a vector of modules that it will recompile, and this is the cross-module symbol provider that does this thing that we get a name and it has a postfix with the module hash, and so we get the unpromoted name and the module hash, and if the module hash is empty, then we know, okay, we have a function name like printf or something that needs to be resolved from our host process, because they also arrive here. We need to separate them somehow. So everything that has no module hash is not of our business. We just say we don't have an address for it. It will be resolved from host system, from the host process, and then we can get the permanent module record for this hash. It's called permanent because it's always there. It will store, it will manage all the revisions for that module. And in this module record, we now search for the latest definition of this symbol name. So it will go backwards through the revisions and get me the first instance of this symbol and returns it. And otherwise, I don't know. This should not happen, ideally. So this is the symbol resolver, and it is used for every module. And here is exactly this link combined modules. We had this earlier. It gets the main module and returns the combined module, and this is what we give to the JIT. It will emit the code, it will optimize it, emit the code, and we store the handle. Of course, we need to store the handle. We don't want this to disappear because we don't want to invalidate any addresses that we have already somewhere in our code. Yeah, and then we're done. And here there is this private variables renaming thing and my own existing definitions turning into declarations thing. That happens here. And there's a lot more code that is probably better to understand by looking at it and checking. Yeah.
How does the replacement of alt handles work? Is it runtime direction or?
How does the replacement of
alt handles?
The function handles that I give out to the main CPP. Well, that's actually also maybe an interesting, maybe a tricky part. It's also a lot of code. So what I have is for each module that I know by ID. So this integer distance is s, for example. I create a permanent module record, and this will always stay there. It will have some place on the heap, and it will not move and not do anything, so I can use pointers to that. And this permanent module record has a number of function records, and they are always shared pointers. So they have shared owners. They are somewhere else on the stack, and if all owners are gone, this record will be deleted. So if I have my function handles that I give out, each of this function handle is basically only one shared owner of this function record, shared pointer. So if all these function handles get deleted and my permanent module record decides it doesn't need this function anymore, it will be deleted. If one of them keeps it, it stays there, but it can be invalidated. It can be invalidated because when I have access to this this permanent module record has access to the function shared to the shared object that is always also at the same point in the heap. It has always this shared pointer until it says here. This is this add function. Exactly. It finds the function. It says, is it compatible or not? If it's compatible, it does invalidate it, which will delete the cached address it stores inside. And the next time I call into that, it will call back to the permanent module record, which it has a pointer to, and say, hey, I need a new pointer for that name.
So
because
a cache miss.
exactly, yeah. So this invalidate will delete the cached address, and so it will query again for the name.
But doesn't that mean there's always some runtime overhead for calling function?
For the first call, there is a runtime overhead. For the second call, it's an indirect call.
Okay.
So you call a function that calls into function pointer. It's overhead, but I think it's kind of acceptable. Like, it's not so bad.
I'm just wondering about things like
Yeah, but-
and so on.
Yeah, this is a good point actually. The goal with this was also to optimize for the call case and not for the management is a bit more heavy now, and also memory usage is a bit more. It could be more dense, but I think call, as you said, is the more relevant thing to optimize for call performance than for management overhead. Exactly, and here is this case where the function gets outdated and shared owners may still call it, but it should return an error then in this case. But this is not implemented yet. Any more questions? Yeah.
Two questions. So first of all, this ThinLTO, it compiles or builds a call graph, but how it works for function pointers and virtual calls?
Exactly. There is, I think, for everything that. How was that? Actually, that's a part of ThinLTO that I did not care about, so I'm not into that so much. But there is a CFI tracking. Don't know if I find that location now very fast. Let's have a look at. Oh, sorry. No, I want. Yeah, it doesn't find the header for that, and I don't find it either. There is a mechanism for that, but actually I don't know. I could show you the location in the code that handles these situations, but I don't know how it works. I don't know.
But would it work like in any situation, or?
What exactly would work in
I don't know, like a virtual call, for example. Would it build the call graph, like the right call graph for the virtual?
I think whole program devirtualization is not implemented yet. So it handles virtual calls somehow, but it cannot optimize through and say, okay, this virtual call can definitely be optimized away because I know, and so on. It does handle it in some way, but I don't know.
Okay. Second question.
Oh yeah, second question.
Go ahead.
Yeah, you said that it can be parallelized, but let's say a function A is about to inline function B, and function C is about to inline function A at the same time, like in parallel, right?
Mm-hmm.
So which, how does it handle this situation? If
Function C will import function A and B, and then it will inline
but
B and A.
It doesn't know yet. The function A did not inline the function B yet, because it's in parallel.
Yeah, but these decisions are first the summaries. The call
Or it
grabs.
doesn't do inlining immediately, but rather builds the graph and then inlines.
It gets the graph from the compiler. It gets the graph and knows who calls who is called from where, and then, like, if you have a dependency across multiple modules, you would say, okay, I import, like you had this case with the 3 modules ABC, and A, how was it, inlines B,
and C inlines A.
C inlines A. Exactly. Then the module that has A would import B, inline this in its own scope, and the module C would import A and B and would do the inlining on its side too. So it's completely independent from each other.
Yeah, but if the C comes first and inlines A, which is
yeah, but this
inline
all these decisions are made during analysis time, and in the parallel
so
transformations, they happen independent of each other.
okay, thanks.
But otherwise, I think it's just straightforward inlining as the compiler would do it. Yeah.
So the goal is to update the code of the running program.
Yes.
But if you have like data structure changes, like you change an int to a double, or you have a structure and you change the order of the numbers of the structure, then all the code will be updated, but the current data will not.
Yeah, exactly. That would be then the good question, or that would be an interesting thing to solve if all these changes could be, or how well they could be merged into the new state. Like you change the representation of your state, and now you have an old state that needs to match to this new representation, right? So you change the variable type, you change the name, you change the order of members of the struct or something like that, and you have an old state that you have a full description of, and you have a new state that you have a full description of. And this is, sure, it will be a million cases where this will not work well and not work easily, but I could imagine that to some extent this could be mapped to each other. In many cases, if you just turn around the order of members, for example, you can realize, okay, this order changed now, so I will map this to the old data, or I will change my data in this. No, I cannot change
I
it.
think then
yeah,
you want to keep the old function around, so they can operate on the old data, and then
this old function would then be a dependent on this change and needs to be recompiled. So everybody who reads that data would need to be changed because the dependency changed. Yeah. But this is, like I said, this is like possible, whatever. It would be an interesting thing to try, but I don't know if it would work. I could imagine that if you had a Git-like revision management system, then you could make rules, a lot of rules that do a lot automatically, and you could leave the developer to do the rest for you. But there will also, with what I didn't mention, I think this will never work for whole C++. When you have like pointer arithmetics or things like that, it will be very fast that you cannot map states to each other because they are just random data.
But in the end, you would have you could upgrade your HTTP server to the next version without stopping it.
Yes.
So Erlang, for example, it does some similar thing where you can patch the code and I don't know how they do that.
I think it's a virtual machine and it has references, and it can say, it does not have addresses and pointers, and it can say, okay, this reference is not that, but this now. Yeah, I heard about this in Erlang, but I think it's, yeah, actually I don't know much about it, so I cannot really say anything about it. Yeah, but I've heard of that too.
This may be a dumb question, but is having org JIT important for your work, or you could use a simple one?
It's important because, for example, I can easily fine-tune the inlining threshold for my optimizer, which I would not be able if I used MCJIT, I think. Maybe it's also possible with MCJIT that you can fine-tune the optimization pipeline, but I think you can just control the path manager or something. I'm not sure. But in general, you can very well say which symbol resolver you need for internal symbols and for external symbols in org. So that makes it very well suited for this case, yes, I would say. I think it's much more complicated to do the same with MCJIT. Any more questions? Okay, you can always ask afterwards. Thanks for coming around and be here and listen to all this stuff. Yeah, thank you very much. That's it.